In lesson 66, we're going to learn about signs of fractions and have a refresher on 30, 60, 90 triangles from geometry, if you were in my geometry. Let's look at this fraction, negative 3/4. Well, ultimately what we're saying is negative of a positive 3 over a positive 4. Because remember, if you have one negative sign, then it's negative. If you have two negative signs, the negatives cancel and become positive. So we simplify this as negative 3 over 4. But what we want to teach is that any two of the three signs can be changed without changing the value of the fraction. So if I had negative positive 3 over positive 4, I could change two of the signs without changing the value. I could change that to a positive negative 3 over positive 4. I changed these two signs here. But notice, this is still a negative fraction, this is still a negative fraction. So these are the same. I could also say, if I go back here, positive 3 over negative 4. These are all the same. But notice from this point, I simply changed this sign and this sign. I kept the third, but I changed two of them, and they had the same value. So any two of the three signs may be changed without changing the value of the fraction. So let's look at some examples. 66.1 says 1 over x minus 3 minus 7a over negative x plus 3. Simplify that. Well, we're going to implement what we just learned. I see that this is a negative x plus 3 and this is x minus 3. Well, we know that we need common denominators to add the numerators, but, and that's a big but, what if we just implement what we just learned? We can change two of the three signs. And so we go from negative 7a over negative x plus 3 to positive 7a over positive x minus 3. Now I know I changed three signs, but what actually happened is this is its own identity. So when I change, the negative 3 doesn't affect the value here. It's the x that does. So when I changed this one, I actually had to change that one as well. But I changed these two signs ultimately, and then this one just went along with the identity of the sum that I had there. So hopefully that makes sense there. But now we're left with 1 plus 7a over x minus 3. They have the same denominator, so simplified it'd be 1 plus 7a over x minus 3, and that'd be your simplified answer. But you can change two of the three signs, and then if you have a sum here, an identity of its own, the third one changes automatically. So let's look at the next example. Wants us to simplify here, or add them together. We have 3 minus x. Well, what I want to go ahead and do is I want to switch those. I want to switch that to negative x plus 3. Because now I can see the x in front. That's easier to see and read everything. From this point, we change two of the three signs. I change this one to be negative, this one to be positive, and once again, if I change the identity here, I'm switching there. The negative 3 being switched from a positive 3 doesn't have to do with the rule we just had over here. Those are different, and I know that can probably be confusing. So from this point, we have 4x. We can basically put all these, we now have the same denominator. So we can put them in the same numerator and add like terms. 4x minus 2x is 2x. And then 5, let me back up, put it in reverse, Terry. Back it up. Do have to say this. When I make this top negative, like I said before, I am making the identity of this sum, 2x minus 3, I'm turning that whole thing negative. So what I'm actually doing is I am distributing the negative to both. So this is actually going to look different. What we're actually going to have is, I'm going to rewrite this part. We're going to have negative 2x plus 3, because negative and a negative. Just like I said, this negative affects both of them there, because it's its own sum and identity. And this is all over x minus 3. So when we add them together, we get 4x minus 2x is 2x, 5 plus 3 is 8, over x minus 3, and that's our answer. And that's how you do some different signs of fractions. The next concept in this lesson is 30, 60, 90 triangles, and its formula. We've done these before, and 30, 60, 90 is an awesome shortcut when you have right triangles. 30, 60, 90 triangles, its principles are that the opposite side of the 30-degree angle, aka the short leg, is what you can think of as your starting point, and we're going to call that x. If you know x, you can know the hypotenuse and the long leg just like that. So from here, if we know x, well, the hypotenuse is always double the value of x. So that would be written as 2x, and the long leg is always x times radical 3, the short leg times radical 3. So knowing that's our formula, looking at example 66.3, it wants us to find x and y. It gives us hypotenuse of 5, it only shows 60. Well, triangle sum theorem, we automatically know that's 30, because 60 plus 90, 150, yada, yada, yada. So now, we have a hypotenuse. Like we said before, the short leg is what gives us everything like that. So how can we get from the hypotenuse to the short leg? Well, in our original principles, to get from the short leg to the hypotenuse, we multiplied by 2. So to get from the hypotenuse to the short leg, we do the opposite. We divide by 2. So we can say that 5 over 2, 5 divided by 2 equals y. I'm going to go ahead and put that in decimal. Let's see what it asks for. Oh, sure. It does. Yeah, that's fine. It does the fraction. So y equals 5 over 2. Short leg is 5 over 2. Now, how do we get from the short leg to the long leg? Well, we multiply by radical 3. So 5 over 2 times radical 3. Well, remember, radical 3 is still over 1. It's only in the numerator. So we only multiply the radical 3 times the 5. So x equals 5 radical 3. There's a lovely 5. There it is. Over 2. And those would be your two answers. But that's how you do 30, 60, 90 triangles. I probably used 30, 60, 90 already in polar coordinates and things like that, but that's specifically the formula to use for those.